It's okay? Yeah, sorry. So so the idea of this work was that we wanted to solve some singular dynamics, which in our context are stochastic partial differential equations, where the singularity comes from the fact that we had to some PDEs some random noise, which is some noise, which is a random distribution. And when you want to solve these equations, you can use some different theories, but they all boils down to do some kind of perturbative expansions, trying to do some expansion of your solutions. And the more singular the noise is, the longer the expansion is. And that's why you need some combinatorics, some systematic way to encode these expansions, and also encode some manipulation that you perform on this expansion, like for instance, renormalizations, recentering. And for that, you need some kind of algebra and actually off algebra. So in the second part of the talk, I will also introduce off algebra, so you don't need to have any prerequisites, or don't need to know anything about off algebras, but just explain why they arise in this context. So first, for those who have never heard about PDEs or stochastic partial differential equations, it's just to think of a PDE. So here I put one example, so KPZ equations from physicist Algebraic. And that's an equation which is supposed to, in the limit, to correspond to the fluctuation of some random growing interface. So here you have your the random growing interface. And you could see that the interface is quite rough. I mean, in the sense that it will not, you cannot, it's not differentiable. At least the height of the interface is not differentiable. And the dynamic is given by these equations. So here you have some smoothing effect, or with your Laplacians. You have some gradient term, the dxu, that introduce the fact that your interface have a tendency to growth. And then you have some space-time white noise. Think of a Gaussian process which have independent correlation. So if you take two independent space-time points, then the correlations is 0. So you will see more on this model in the next talk by Konstantin Mateski, who will describe some university class for these models. And but here, that's an object of interest. This is this continuous dynamic, which is quite rough because, as I say, you can see that it's not differentiable. So you get an issue with dxu square. So dxu, the solution is not differentiable in space. And you have to take the square of these distributions, which is also a problem that you are not able to solve, I would say, deterministically or analytically. And the idea was to say that because you are in the stochastic context, you want to exploit the fact that, in fact, all the singularity on this equation, or the fact that it is quite ill-posed, is coming from the space-time white noise. So now I want to move to another example, which is a bit more involved actually in the computations, which is actually a generalization of the KPZ equations for a totally different context. So here the idea is that you want to construct a dynamic taking value in some loop space. So for instance, here you are looking at a loop on a sphere. So here I have just one loop. So actually it's a Brownian loop. And you want to construct a stochastic evolution of this loop. So that's a loop at time t, and that's a loop at time t plus dt. And the way to construct these dynamics is to work with a system in coordinates of generalized KPZ equations. So you still recognize here the Laplace here, the Laplacians here. You have here the same quadratic term, but here you have different coordinates. And then in front of the dxu, you have the Christoffel symbols associated to your Riemannian manifold. And then you have the smooth vector fields, which are connected to the metric. And here is some space-time, independent space-time white noise. So if you want, this is a projection of your dynamic in coordinates on some charts on your manifolds. And so that's a system of equations. And then you want to also give a meaning to these equations as you have the same issues as before, in the sense that this dxu squared or dxu beta times dxu gamma doesn't make sense. There are also more complexities in the sense that you want also to define what you mean by this stochastic product here with the space-time white noise. Here the equation is no longer additive. And also you have extra difficulties that you want also to make sense of this product, but you have also here a nonlinearity in front of this dxu square. So this makes the equation quite complex. And also maybe you want, if you try to define this product, you want to respect some symmetries of the problem. One obvious symmetries would be that you want these equations to be geometric. So if you change coordinates, you still have the same type of equations. or maybe you want some etoisometry here on the products. So these are the two main examples that you have in mind. And this is example actually, the main example that motivate to push forward the expansion of these solutions and to introduce a lot of combinatorics for dealing with these expansions. Okay, so that's the examples. The equations that are written for the moment are very formal because I have space-time wide noise, I have distributional products, I don't know how to make sense of them. So one thing we can do first, okay, we can just try, if we go back, sorry. Here, what we can do, we can try to write a form, if you want, the form of equation we want to solve. And the form is the following. So here I have some differential operator here. Here think of the Laplacians, but could be other operator, but you just need to have a smoothing effect. And we represent the right-hand side as some kind of linear combinations where I have some space-time wide noise, or it could be just one, that would be for KPZ when I have the gradient U squared. And I have some nonlinearity that depends on the solution and its derivatives. So it could be gradient or higher if you have worked with higher order operators. So this equation is extremely singular due to the fact that these noises are random space-time distributions. So one way to start the problem, at least to try to find something that will make sense, is to say, okay, now I will just replace this rough data, which is this random distribution, by something smooth, or an approximation of my noise. So I take a class of modifiers, depending on, then I make them depend on some parameter epsilon. You could see this rho epsilon as some approximation of the identity. So when epsilon converges to 0, this actually will converge to my noise xi I. So I just find a nice class of regularization, if you want, for replacing my rough data by some smooth data. So then when I do so, I just have an equation that makes perfectly sense. So I just work with an equation where there is no problem anymore because I smooth out the noise. So I have a solution which is defined in a classical sense of these equations. And then what you want, of course, you want to say that this solution, defined in the classical sense, you want the solution to converge to a limit. And you will say that the limit in a certain topology will be the solution of my problem. So that's the strategy. The problem is that when you work with the solution maps, so when you are in this classical solution, so you have a solution maps that takes your noise or regularized noise and send it to your smooth solutions, UXL. And you want to pass in the limit in this map. But the issue is that this map is not, okay, sorry, typo, is not continuous in the noise. It will be just measurable. So you want this map actually that, you want to find a topology such that this map is continuous. And by continuous, meaning that you want to pass to the limit on the noise, and then you want to pass the limit inside that map to get your solution. But unfortunately, this map is not continuous, and just having the noise is not enough. You need to add extra data in order to recover the continuity of the solution map. So that's this extra data that actually needs combinatorics, because you need to construct iterative integral of the noise, and you need to add that to your solution map, or to your topology, in order to get the continuity and to be able to pass to the limit. So that's, if you want, the strategy or the main idea that actually originated from already SDEs or rough SDEs, where people also have to add iterative integral of their noise for getting back the continuity of the solution map. Okay, so now what is the strategy? What I have to add to this noise in order to get continuity of my solution map? So the idea, okay, so now I start with this regularized equations. So now I just have my smooth data, and this is the classical solutions. And one strategy is to say, okay, this equation, maybe by some, you can do some scaling argument, especially for KPZ when G and F are equal to 1. And you can say that in a certain regime, you are able to remove the nonlinearity and to just get the linear equations. So in a certain regime, the solution of the nonlinear problem behave like the solution of the linear problem. So when you say, okay, now maybe one strategy would be to say, just develop or use this expansion. The solution of the nonlinear problem is the solution of the linear problem, which is given by this, which is just stochastic heat equations, plus some remainder. And what is nice here is that this, this solution of the linear equation makes perfectly sense. I can pass to the limit on epsilon, and I have a solution, which defined by the stochastic convolution. So this term, it's well defined in the limit. So I can pass on the limit, and I can construct, this term is defined. And now the idea would be, okay, now I use this type of ansatz, which is a natural ansatz in mathematics, like a solution of the linear problem plus some reminder for some solution of the nonlinear problem. The issue is if I do this, so if I take this, it works. For instance, I will be stuck because I can plug this inside, so I can replace U by V epsilon plus W epsilon here. And then I could continue the expansions and maybe try to derive an equation for W, hoping that W is more regular than U epsilon. The issue is that it works if you have polynomial nonlinearity. If you have polynomial nonlinearity, you can expand your expansions and re-expand again using some mild formulations and continue the expansions. Here you are a bit stuck because F and G, if you remember the geometric problem, there are Christoffel symbols, smooth vector fields, and they're not supposed to be polynomials. I mean, they are truly nonlinearities. So in fact, if I just do this global expansion, this will not work. So one idea, or what's the main idea of relative structure invented by Martin-Herrera, was to say that if I want to do a global expansion, this will fail. I need to localize. By localizing, I mean I need to have something, some type of Taylor expansions, which allows me, if I plug an expansion here, I'm able to re-expand using some type of Taylor expansion, like you will do in approximations. And this will allow me to linearize, if you want, my problem, or to expand again my problem. And so the idea is to say that instead of doing this type of expansions, I just recast that in this form, where here I have some reminder that depends on Z, so the point on the points that I fixed. And here I have, if you want, a Taylor jet here, where here is U tau Z is like some monomials in Z. And here I have some coefficients that could be interpreted as certain extended derivatives. So think of, you could think at first approximation of some type of Taylor expansions. But the idea is that because you have U is a solution of a stochastic partial differential equation, you don't expect to describe the roughness of U just by using classical monomials. In the sense that in these monomials, we have also stochastic or recentered stochastic iterated integrals. So when you do this type of expansion, there are different things that you need to prescribe. First here, when I was doing this expansion, I was just saying a solution of the linear equation plus other terms. So I need to prescribe how far I go in my expansions. That for monomials would be the order of the monomials. Here I have a finite set of symbols, or if you want, what's a finite set of monomials. So this would be an abstract set that I denote calligraphic T. And in fact, this set would be a finite set of decorated trees. So we'll introduce on the next slide what are these combinatorial objects which are used for indexing expansions. So then you have these monomials, which are recentering stochastic processes, which are actually they are non-Gaussian, but they are polynomial maps of Gaussian random variables. And so you have the coefficients, and you have the reminder here. You could see that which is small when you are closer to Z. So that if you want some kind of ansatz, and in the theory of relative structures, we are able to say that if you give me this model of these equations, we are able to compute exactly what should be this map, also what are the coefficients. So this is completely systematic by now. So now I would like to talk about these combinatorial sets. Okay. So what we use here is decorated trees. So the idea is that when you try to write a stochastic iterated integral, it could be quite nasty because you need to iterate several times, you make convolution with different kernels. So it starts to be very heavy to write after a certain number of iterations. So that's why having some combinatorial objects to describe them is quite convenient. So then I will present the most simple ones. So for instance, here I have this stochastic iterated integrals, where here I have my spacetime y noise, which has been regularized. Here I have a spacetime convolution or stochastic convolution with a kernel that I denote G. And G, you think of the it kernel. So if you want, this term here is the solution of the stochastic it equations. So of the solution of the linear equation. Then what I can do, I can take that term, I can take a spatial derivative on my it kernel, space-time convolution with my noise, and I can square it. So if you want, this term is coming from It's like I plug v here inside, and I take the square. So this is a term that appears in the expansions. And now I'm using a coding, or if you want, decorated trees coding for these stochastic iterative integrals. So for the first one here, I just the noise here will be represented by this gray dot, and then I have a blue line connected to the root, and the blue line will correspond to a space-time convolution with the heat kernel. For this second term here, I have a squared here, the squared that will correspond to a branching. So here I have two branches of two edges outgoing the root, and I have to use a different color or different coding for the edge, because one edge was convolution with the heat kernel. Now the other edge is convolution with the derivative in space of the heat kernel. So that's why here I put a fat edge, or if you want, a brown edge for coding that. So that's where the term decorated trees come from, is that you put decorations both on the nodes and also on the edges to encode the various differential operators that you use, also the various noises that you can use. So if you want, these are the first terms that appear when I do the first iteration of my equations. And of course, the trees can grow, so I can use more products, and they can have more, can be bigger. And then they just introduce the fact that I have several iterations, and my stochastic iterative integral becomes more complex. Okay, so these are the basic blocks. So if you want, this will be the iterative integrals you may want to use if you do a global expansion of your solutions. But as I say, we are not doing that, because if you want to bypass the fact that we have true linearities, we need to use a local version of these integrals. So for instance, for the first stochastic iterative integral, if I want to localize it around the point Z to make it small when it's close to the fixed point Z, I just need to subtract its value at the point Z. Because in fact, this term, when you pass to the limit, it's actually C alpha order functions in time and space, which is of order 1/2. So by subtracting this, I just make it vanishing at this order when I'm close to Z. So I just need to subtract that term, and this term will be small when I'm evaluated this function close to Z. Okay, so this one is quite simple. I just subtract the stochastic integral at the value Z. For this one, in fact, this one is supposed to converge actually to distributions. I mean, so there is no need of recentering. I mean, because there will be a blow up, so there will be not locally small. So here I just do nothing. I don't need to recenter it. And then, of course, there is another issue, because if you want this procedure, it's just to make sure that when I have smooth data, I'm able to do my local Taylor expansions, and I'm able to do this local expansion of my solutions. But I want to pass to the limit. Okay, here there is no issue. I can pass on the limit. I just apply a linear operator to my noise. I just do this stochastic convolutions. So then I can pass to the limit and have a limiting object. But on this term, here I have a problem, because here I'm taking a product. I have a square. And this square is coming from the ill-defined product of my equation. So in a way or another, I cannot escape that. If I start with some distributional products, they will be there at some point in my expansions. And in fact, they're here. So with this squared, I have to deal with this squared. But what hurts me is that now, of course, I will have to square in the limit two distributions. But these distributions are quite explicit. That's just a polynomial in the noise. So here I can use a probabilistic argument to construct these stochastic iterative integrals. So for instance, for this term, it's quite simple in the sense that I just need to subtract the mean of the term, just these expectations. And then when I pass to the limit in epsilon, this term will have a defined limit, and we'll be able to construct the object. So here there is a bit of a twist, is that here I have some recentering. So I want my stochastic iterative integral to be small around the point Z. And then if you want, here I have some stochastic recentering. So I want in the end my object to be of expectation 0. So there are two procedures which seems, I mean, they are a bit of different nature, but in the end it looks a bit the same, okay? But for two different purposes, but they look a bit the same. So here what I've presented is really, if you want, a toy model, or if you want, the first iterative integral. I And if you look at this one, they are not very complicated. I just, these three, there's two edges, one and two nodes. And you could see that you can easily, I mean, there is some work, but you can propose quickly a way to recenter this iterative integral and also a way to renormalize them. But also it could start to be quite complex because you need to perform the two operations at the same time. So you need to do recentering and you need also to do renormalizations. Here it works well because here I'm doing recentering, but I don't need renormalizations. Here I do renormalization, but I don't need recentering. So if you want, in the two cases, I have not cheated, but in fact, I just presented two stochastic integrals when one of the operations, either renormalization or recentering, is not there. So I don't have the issue of doing the two at the same time. But in fact, for stochastic iterative integrals, which are bigger, if you go higher order in your expansions, actually the two could be there. So in sense, you have an iterative integral where you need to do the two operations, perform the two operations at the same time, recentering and renormalizations. And then they start to be a mess because you say, okay, now if I try to make my term small around Z, but I want also the convergence in epsilon, those one will not destroy the other. I mean, is it possible to do the two at the same time? So it's a natural question, and one can wonder if it is possible and that you need to be extremely careful. And actually, we are able to show or to see that actually we can do the two at the same time. So what I described it a bit unwaving, you could see a very abstract context, in the sense that the two structure here, which is recentering and renormalizations, you could see it as abstract context as some off algebras on these decorated trees. And the fact that you are able to do the two at the same time is because you have some interactions between the two off algebras. So in the fact that co-interact, I will explain what it is, they co-interact nicely, which makes the fact that you are able to put the two operations at the same time. So this was the object of this paper, is to start from this, I would say, examples, where you are able to do the two operations that are needed for defining these objects, and to put the correct combinatorics for governing the higher orders, if you want. So I would say that in that case, working out examples is the best way to get intuition of what should be done at higher order and what should be the good structure that will emerge from this analytical or probabilistic computations. Okay, so before moving to the algebraic side, I would just to do a brief recap of actually what's happening in relative structures. So what's happening is that you start with some noise here, and you start with some equations, and then you have some solution map that they did not phi, which is not continuous in the noise. That's why I put it in red. And what you do is that you lift your noise in some object that we call a model. And the model, this is all these stochastic iterative integrals, which had been recentered around point end. And if you want convergence, this model has been to be renormalized in the sense that I have to, this one I don't need, but this one I need to subtract the renormalization constant. So I need to tweak a bit my model to renormalize the ill-defined products. And then I have a solution map, which is in green, which will be continuous in the model. And this is where I can pass to the limit. But if I change the model, if you change the topology, you change the nature of the product of the stochastic iterative integral, in fact, it's like in physics, you are renormalizing Feynman diagrams, you need to change Lagrangians from which you build up the Feynman diagrams. So you need, in fact, to go back and to see that actually this renormalized model originates from a different equations where you have an action of renormalization of these equations. So for instance, in the context of the KPZ equations, I have to add here a counterterm that corresponds to the renormalization that I have put at the level of my expansion, or if you want, of my stochastic iterative integrals. So the transformation that I'm making here on the model, they will be reflected here at the level of the equations. So if you want, this is what we call a bottom-up approach. Or you could start by saying, okay, now I put the correct ansatz here, and that produces the correct renormalized each stochastic iterative integrals will be a top-down approach. So it's that in the Lagrangian, you put already the counter terms, and then when you do your expansions, you get all the terms renormalized. Okay, so that's, if you want, the general picture of what we achieve, part of it we achieve in this paper. Yes, for historical purposes, I just present the papers. So if you want the first one, just introduce a diagram. This is the one I present, introduce the fact that you are able to construct this stochastic iterative integral with using some of algebras. Here you have the convergence part. And the last paper, implement the renormalisation as a level of the equations. So for the remaining time of this talk, I think it's around 15 minutes, I would just focus on the algebraic part. Yes. So first, I need to introduce the algebraic object, and I think most of you don't know it at all. And I didn't know when I started to work on this project. And just to remind you what is off algebra and what is useful for. And so first, you start with a unital algebra. So you have just a product and a unit, so that's easy. So I think most people have seen that. And then you work with, you introduce another map, which is a coproduct, sending H into H tensor H, that satisfies the property of coassociativity, which is this property. So this would start to be a bit scary, I introduce tensor product and so on, but you're just to see that this property is called coassociativity because it's, if you want, similar to associativity, okay? So it's, for algebra, you have associativity. For, when you add a coproduct, you have coassociativity. So this is reflecting that you can do the operations in different orders, actually. You have also the definition of a counit, so that's just the dual of being a unit. And one interesting thing is that if you have these properties here, you don't have actually off algebra, but a bialgebra. Instead, you have coproduct and product. You need to have another map, which is called an antipode, could be seen as some inverse. So in sense, here I have two identities that tell me that I have an inverse, right inverse and left inverse. So if you want, it's like if I give me some type of inverse. So I will explain why this map is so useful on the next slide. And if you have all these objects, then you obtain what we call off algebras. So why this structure is needed in what we are doing? Because it's quite complicated, many operations and so on. So first, for the coproduct, you have to think that the coproduct is taking an element and split it in two parts. So you have to think, for instance, when I'm doing renormalizations, I'm taking expectations. So if you want, this is detaching some parts of my trees or computing these expectations. So this is why you have these operations. Or when you do recentering, you evaluated part of your stochastic iterative integral at some point that. So also it's detaching a part of your iterative integrals. So in a way, you will need a map that allows you to split your combinatorial objects in two parts. One when you apply the expectation for the renormalization, or one where you will evaluate this part at a certain fixed point. So that's, if you want, the way you could see why you need a coproduct, but why you need an antipode. So the antipode, if you want, is because we have some recursivity in the procedure. If I do recentering, I may want to do recentering again. If you want, I have to have some recursive procedure. The same for renormalizations. If you think about Feynman diagrams, I may have a divergence, also some subgraph which is divergent, but then I may have something inside also which is divergent. So I want to repeat the operations. And the antipode, actually, here I haven't written it, but you can write some kind of recursive formula for the antipode, allows you to repeat the operation again. So if you want, here you have already tools that reflect or could help you formulating the operation or iterating the operation that you are doing. There is another aspect which is very nice about off algebras, or at least we use heavily in this work, is that you can construct groups on the group of characters. So what are characters? So you are looking at element linear maps on the dual. So that send H into, let's say, R. And you want this map to respect the product of your algebra. So they are multiplicative map. And you can equip these linear maps, or these elements of the dual, with some product, which we call convolution product, given by this star. And the convolution product is computed by the coproduct. So I split my elements in two parts, and then one is fed to G1, and the other one is fed to G2. And in fact, that the coproduct is co-associative, give me that the fact that this convolution product is associative. So then I can have an associative product on my space of characters. So why the characters are helpful? Because characters, you have to think of, I take my tree and I send the tree to a stochastic iterative integral. Or if I evaluate it at a point, it would be something in R. So in a way, when I have the character, it's just dissociating, if you want. I have the combinatorial part, and I send this combinatorial part to an analytical part, a stochastic part. And this is done by these maps. Okay. And then you can also compute, if you want, the inverse for this product, which is given nicely by the antipode of the Hopf algebras. So to a Hopf algebras, I can associate a group of characters. And these characters are helpful for defining my stochastic integrals. So then I could have a group structure on the operation that I'm doing. For instance, if I'm doing renormalizations, I presented an example where I subtracted the expectations, but I could subtract maybe something which is for finite value. I could change it, I could perturb it. And this I could interpret it by saying I would maybe take another element of this group of character, and I would just do my convolution product with this in the group, and I would change the nature of my stochastic integrals. The same for the recentering. For the centering, I say, okay, now I want to recenter around the point that, but maybe I want to change the point in which I do the recentering. So again, I will take an element of my group of characters to re-expand or to change the expansion, the point of the expansions. So in fact, with these constructions, in fact, you just need to know that about for our work, like just this definition that I put on these two slides. You are able to construct two groups. One is a so-called structure group in relative structure used for recentering your stochastic iterator integral. And the other one, which is maybe not so nice formulations because this name existed before, it's a renormalization group, but different from what people think about renormalization group. Renormalization group in terms of characters that are presented here. Okay, that was, if you want, the definitions that you need. And in practice, here I presented the two of algebra we used, but I didn't present the full definition because it's quite heavy. There are decorations everywhere. We play with decorations, but just basically the idea. So of course, I want to take H to be the linear span of the decorated trees which I use for describing my solutions. Unfortunately, this H is not actually an algebra, because if I could multiply elements, in the sense, I mean that I don't have distribution. I mean, the product should reflect what I have in my equations. So I don't have Hopf algebras, an algebra on that, but I could have two algebras here that will act. This would be a module over these two Hopf algebras. And then I can define two maps. So I have an Hopf algebra which is generated, freely generated by planted trees of positive degree. So by planted tree, I mean trees which are just of this form. Yes. So that's the planted tree. So remember, this was a term of this form with epsilon. And so then what I do, I just do the free product of this element. So I take product of terms of this form, and you can put also derivative on the kernel if I want. And I want all these terms in the limit, they need to be functions. So each term in the product, when I pass to the limit in epsilon, should be a function. So that's what I mean by positive degree. Then I could do the same, but for the free algebra generated by negative degree. So for instance, I could take an element of this form. Okay, here I will put maybe, instead of brown H, I put this term. So if you remember, this term was this. And if you want, I can take products of this. I can take this one again. So I take the free products. I just got a collection of trees, which are actually a forest. And I ask that this tree of negative degree, that they converge to distribution. So they are problematic. So this is, if you want, this H minus. And so now I have, these trees, and now I perform combinatorial operations, two different combinatorial operations. One, which is written on the top for the recentering, I'm extracted a tree which is connected at the root. So here I put the tree in blue, and it is extracted here on the left, and then you have a contractions here on the right. So why I have to do this operation? Why this operation will actually correspond to a recentering? The idea, if you want, what I'm doing here is some kind of local operations. Because what I'm doing here, I'm doing a modification that touches the root of the tree. And that corresponds to the idea that when I'm doing recentering, this is a local operation. I do a recentering toward a point. Then the other of algebra, it's a bit more complicated. is more like I've identified a sub-pattern in my tree of sub-iterated integrals that are badly defined, and I want to extract them, which are given here. And if you want each of these terms, will be actually, you apply expectations. Just if you want, there are renormalization constants. And then I contract everything inside the tree. So if you want, this is an operation which is non-local, because I can extract terms or subtrees which are not attached to the root. So they could be everywhere. They could be also as a root, but they could be everywhere. So if you want, here I have a local operation, which is just extracting a tree of the root. Here I have a non-local operation that I can extract, if you want, different subtrees, which are disjoint, it's a subforest, at different locations inside the iterative intervals. So that if you want, that's a two coproduct that we use for doing recentering and renormalizations. And that's the main result of the paper, is that if I look at this recentering coproduct, in fact, I have some right module structure. So H, the space of decorated trees. You have some right comodule structure over H+, which is of algebra. You have the same structure for the forest, for the negative of algebra, but this time is a left module. So in a sense, it's a different direction. Here it's on the left, here it's on the right. So one is acting on the left, one on the right. So then you could imagine that maybe you can do the two at the same time because they're not acting on the same locations. And in fact, you have the third property that says they cointeract, which is at the level of the groups, give you these actions. So here I have two convolution products on my characters, and I have these nice actions that allows me that one group acts some type of semi-direct product between the two groups. So in fact, I can act with my renormalization group on the recentering group. So this is encapsulated in this nice formula. So if you want, in plain words, without talking about algebra, it's just at the analytical level, you are able to do the two operations at the same time. So you are safe. So that's, and with this, using these characters and these group relations, you are able to define properly what is the recenter model, completely independently from the size of, or if you want, the number of terms you have to deal in your equations. Okay, now I want just to say, or you could say some examples. So for instance, for the structure group, the groups acts on H. So in fact, you have this formula where you have some character which is used here for the right-hand side of the coproduct. And if you want what I call a structure group, because you have a right module actions, it's just this representation where I take element in my group of characters and I construct this gamma F. And here, briefly, I put, yes, and then what you do is that you define your recenter iterative integral by choosing a correct character that you put here. So if you want, this will be the evaluation at the point Z, or interpretation of your stochastic iterative integral at the point Z, such that if I tested the type of function which has been localized at the point Z, I got the correct behavior that depends on the degree or the regularity of the stochastic iterative integrals. And here below, I explain that you could do a re-expansion map. You can change the point with some map x, z, y, which is constructed from this character and the inverse for the convolution law. So time is running fast, so maybe, yeah. And here I put some examples. For instance, for this one, what does that mean by extracting a tree as a root? So I extract the full tree here, or I can extract just this node. And here I can do only this. So I can just extract that tree. And here I've computed the degree, or if you want, the regularity of each terms. And here also I computed what should be the character, which is actually the answer that we find before, which is just a convolution with the kernel and my noise. And then I can define, yes, so I can define this map is defined in this way. And then if I want to iterate, I need to put some type of antipode for recursively compute the recentering. You can do the same for the renormalizations, where you have this map. This time is on the not on the left but on the right, and I have the same type of representations with my group of character. And now I have to choose a character that would actually compute the renormalizations. And in first approximation, you can just take the expectations, but it's not enough. You need to apply also some recursivity with a twisted antipode. And this is what we call the BPHZ character. because it allows you to have like a recentered stochastic iterated integral in the stochastic term. So if you take the expectation of this renormalized stochastic iterated integral, it is 0. So if we want, this is a good choice for this character. And here I put some examples where here I have to extract a tree, so here I have only 2 terms. Here I have more combinatorics because here I have this subtree appear twice, so I have a factor 2 here. And if you want, this is a term where I contracted the tree on the right. And below you could see, well, that I interpreted that term. I put an expectation here for the renormalizations. And for one of these, I just put also the expectation of the term. So if it is a Gaussian processes, this one will be 0 because I have 3 noises. And this one will survive and put the correct renormalization of the stochastic iterated intervals. So inside this stochastic recentering could be interpreted using these maps and the characters that I have introduced. Yes, I would like to finish on some remarks. Is that what I presented, it was really the general theory. You construct these expansions. Algebraically, you are able to do recentering and renormalization at the same time. What I haven't told about was actually you need to show convergence. So I say you need to put these expectations, but then you need to prove actually that this is convergent. But you can do it. But actually what were remaining the main challenges, because then with this you construct a systematic way to solve a large class of singular SPDs. One question was equation with symmetries. So as I talked about in the introductions, if you want to preserve some symmetries with your renormalization, because renormalization would change the equations and may change, and with the symmetries you want to select the correct element in the group or the correct character that actually will respect the symmetries. So there were some subsequent work that where we deal with stochastic geometric equations, and even more recently with Vladimir Osenko, we use more algebraic tools like for dealing with the chain rule in the context of SPDs. Or you have also this Yang-Mills 2D and 3D, where also the choice of renormalization is important for guaranteed gauge invariance. So also on the algebraic side, it's developed a lot. So here I've just presented the off-algebraic side in this paper, but you can see more structures that allows you to reduce, instead of having this coproduct, which is quite complicated, you can start with more elementary structures. And also now we also gradually move up to the level of the type of algebra we use, up to homological algebra for dealing with these symmetries problems. There is also type of expansions that Yvain mentioned here. Here was mostly on decorated trees, which is a natural way to encode iterated integrals. But I can use another index set, which is extremely helpful in a one-dimensional problem, which are multi-indices, which were introduced by Felix Otto and co-authors. And also there you have some nice algebra structure for constructing this recentered or renormalized multi-indices. And also one last application is that you could use this type of local expansions because they are reminiscent to numerical analysis, and also they appear in renormalization of Feynman diagrams. You could use them for building up numerical schemes. So that's also an application. So you could use this for numerical scheme, and I did that with Katrina Schrass for dispersive equations. So I would say the challenge now, it's just, of course, there are many directions, many applications. But actually, I think that I believe these tools, which actually originate, the two of algebra that are presented are coming from Kramer and quantum field theory, and also they've been used in numerical analysis. The tools that have been developed in this singular SPD context will actually be export or used in other fields for trying to govern expansions which are similar but still different on the analytical aspects. And I think I will conclude on that. Thank you for your attention.
Okay. Questions? So this gives you a systematic way to proceed. So usually in the first equation, like KPZ or even the geometric case, there was only a finite and so very big but number of terms to renormalize. Can you handle like an infinite number in this way?
No, infinite number, we are gone. I mean, there's no way. We can be arbitrarily close to the critical value. Then the number of terms will explode, and when you are get close, you get a lot of terms. But it should be always finite, because it's part of the topology that we use. I mean, we use a topology where we put the noise, and then we put extra terms, this topology, and then we have a finite number of terms, and then you pass on the limit on this map, which is continuous in this finite number of terms. I don't know if you can put a topology with a finite number of terms in this way. So that's one of the limitations because we are building up solution theory of this type of expansions. But if you put some parameters in the system, and according to this parameter, you try to play and try to repeat some type of expansions, maybe by playing with the parameters, you could make sense, potentially, I don't know, I have no idea, of an infinite expansions, but maybe not for the solution theory. I don't know, but maybe for other purposes, but maybe not for the solution theory.
Okay, more questions?
Sometimes when we study the singular SPDE in the Rn in the whole space, sometimes we will introduce some weight to define the solution and the noise. So in your algebra structure, can you content this situation?
Okay, so the work that they maybe didn't mention was only on the torus. So, yeah. So if you put weights, the algebra structure remains the same, just that this is robust. It's that the definition that will vary will be the way you define the characters, the choice of characters. This is in this character that you may have to use a weight, also in the interpretation of the combinatorial objects. Is that what you observe is that it turns out that this algebra structure that we introduce is quite robust to many contexts, that by just changing a bit, you are robust. It's just when you use the correct characters, this is where actually you interpret these combinatorial objects as analytical objects. You may want to introduce this weight. This is where you have the analytical part. So if you want, we detach the combinatorial part from the analytical part. It's just with the characters that make the connections between the two.
Okay, so, thank you.
Okay, do we have more questions? Okay, if there's no more questions, let's thank the speaker again for the wonderful talk. The next talk will start at 2:45. We'll probably have 30 minutes break.